All right, hello and welcome. In this little video, I'm going to be doing a introduction to Geiger Muller tubes, how they work, and then I'm going to show a few experiments that we did here at the University of Utah that use a Geiger Muller tube. So with that little preamble, I'll get started. And before we really dive into the technical aspect of this, I wanted to do a brief history. So this whole process of detecting radiation was actually invented by Hans Geiger in 1908, and Geiger Muller tubes were later invented in 1928. These were used extensively in the study of radioactive sources, as most people know, and consequently, this device has actually saved countless lives. I would not say it's a exaggeration to say this has saved millions, if not even billions of lives due to their use in instances such as Fukushima and Chernobyl and Hiroshima. So, um, interestingly, this also provided an eloquent way of observing simple quantum mechanics at work, as we saw a lot of the distributions that were proving the types of particles we're seeing could be classified. So this is pretty interesting, and I would say a very large discovery. But let's move into the work that we actually did in the lab and how the Geiger Muller tube works. So this was our experimental setup. Here's the Geiger Muller tube. And what we ended up doing is we sent data from the Geiger Muller tube into some sort of counting mechanism, which then communicated through means of a GPIB bus to a computer that was running a remote desktop. So we could actually interface from our own home with a Geiger Muller tube, and we just needed the help of the professor. And yes, we were using a software called LabVIEW, which is used quite extensively. So as far as the actual operation of a Geiger Muller tube, let's go into this circuit here and explain how this works. So the Geiger Muller tube is essentially, we have some sort of metal wall here, typically. And some Geiger Muller tubes have a micro window, which is specifically designed to let lower energy particles through. And inside here, you have some sort of gas, which acts in some ways almost like a scintillator. Now, this is typically some sort of gas that can become ionized easily. And you can refer to the internet to find the specific materials they use. But nonetheless, inside the middle of this tube, we have an anode. And this is brought up to a very high voltage, roughly around 500 volts, sometimes even higher. There's a resistor in line here so that there's virtually no current flowing through this. This is just at some very high potential. Now, on the side of this metal wall, on the outside, we have the cathode connected, which is connected to ground. So we basically have a bunch of negative particles lining up here, electrons, that will gather on the side here. So we essentially have a capacitance between the anode and the cathode. Now, these particles will typically accumulate on the wall of this Geiger Muller tube, and you'll see that this plays a key role in just a moment. So, what ends up happening when a radioactive particle is emitted from some source? It will travel through. If it has enough energy, that is, it will travel through into the Geiger Muller tube, and it will enter this gaseous substance and actually cause a avalanching ionizing effect. This is called Townsend avalanche, and you can find a lot of information about this on the internet, so I won't belabor the point. But what ends up happening is you have all these electrons, and they get generated in a photomultiplicative effect, and you end up creating a voltage that's actually high enough to cancel out the voltage on this anode. And so you end up with enough particles that all the particles that were accumulated here are canceled out. Now, the voltage on the anode is zero for a small amount of time. And when this occurs, the negative particles that were accumulated on the cathode, they essentially want to recombine in the center. And this creates a voltage difference here, or I should say a current pulse, really. It creates a current pulse through this 470K resistor. And we can use a device such as a counter, or even if we wanted a digital like an ohm reader of some sort, you can detect this current pulse. So that's essentially what occurs. Now we allow tons of particles to come through, and any software that we have hooked up to this device will be able to detect how many radioactive particles we're receiving in a given amount of time. So this is just one design. I've seen several others actually. They're all very similar. But if you want to find a more in-depth explanation of a Geiger Muller tube, I highly recommend checking out this YouTube video. He does a really good job of explaining it succinctly, and I definitely think he does a better job than I have here. So without further ado, though, let's move into some of the experiments that we did. So first, we're going to talk about how we can determine the dead time of a Geiger Muller tube. Now, what the dead time is it's the time it takes after a particle comes through into our system and gets rid of, or I should say, it. What's the word I'm looking for? Discharges the Geiger Muller tube. There's a small amount of time required for our, tube to be able to restore itself and be able to sense more radioactive particles. So that is the dead time, the time it takes to restore the tube's ability to detect radioactive particles. So what we did is we hooked up an oscilloscope that was monitoring the voltage at, I believe this is the cathode. Let me make sure I get that right, just a moment. Yes, it must be the cathode because it's only 500 millivolts. And we're looking at this first pulse. This occurs when we have our radioactive particle come through and discharge the system. We get a small pulse. Now, after this pulse occurs, there's a small amount of time you can see here where the voltage at the cathode is actually just going to be completely 0 volts. And then it starts to charge up again up into the threshold voltage. So this time between when the charge begins to accumulate again, that is the dead time that we're measuring. And here with the settings that you see right here, the high voltage 500 volts, the threshold voltage at 1 volt, which we can tell from the graph, and the source a distance of 15 centimeters away, we measure the dead time to be roughly 350 microseconds. We could get a more accurate value if we actually use the cursors on the oscilloscope, or even if we save the trace data that this produced and actually just graph that in Python or something. But nonetheless, this is roughly the dead time we have. So we know that if we set our counter to look at a rate higher than this dead time, that we essentially won't be getting accurate data. So we need to allow the tube to charge up again. So the dead time is important in the operation of a Geiger Muller tube, as you can see. Now, moving to the next experiment, we were able to look at the rate versus the high voltage. And so varying the high voltage on the anode, we can see that the number of counts per second, or the rate, plateaus. Now, I was a little bit confused as to why this happens, but as far as I'm concerned, this basically occurs because, so the reason why this occurs is because we have the high voltage set so low when we're down in this lower voltage here that particles with less energy are able to trigger our system. And so this causes us to just count more events that aren't necessarily radioactive events. So when we have a higher energy level, such as those coming from alpha, beta, or gamma particles, we're able to detect these. I don't know actually if the Geiger Muller tube can detect alpha particles. I think those would have to travel through the MICO window in order to be detected. Nonetheless, that's the rate versus high voltage experiment. Now, another experiment that we did was the rate versus distance. We had the high voltage and threshold voltage set, as you can see, and we allowed the rate, we measured the counting rate versus the distance of the radioactive source to be measured. You can see that at a further distance, the counting rate drops. Now, this makes sense intuitively because we're decreasing the intensity of the radioactive particles incident on the Geiger Muller tube as we increase the distance away. You can imagine if we move the Geiger Muller tube 1,000 miles away, we would probably never get any counts, at least from that source. So you can actually, as I'm not certain about this was part of the assignment, I believe you can use this to determine the mass of the radioactive material because of its relation with intensity. So we know, for example, that if we can measure the intensity at the source, then we know roughly how many radioactive particles are coming from this source at every second. And so I think we can use that to essentially say there must be this much radioactive material. And consequently, we could detect the half-life in this manner if we knew the amount of radioactive material present. But more discussion on that in the near future. So another experiment we did was the mean count versus the gate width. So we essentially just measured the average count as we increased the gate width, the amount of time that we were analyzing our system. So, whether it was maybe 5 milliseconds or 50 milliseconds down at these points, or a higher amount of time, such as here at 1 second or 3 seconds. You can see that the mean count increases essentially linearly. Now, we didn't have a lot more data for this particular experiment, but I'm almost positive that this trend will begin to increase. And it makes sense intuitively as well, because the more amount of time that you sit there and measure something, the more amount of time that you sit there and measure radioactive events coming from a source, the more counts that you should see. And that should increase linearly. So another experiment, we were able to measure a Poisson distribution coming from the Geiger Muller tube. And this is to be expected because what we're trying to measure here are cosmic rays. So what we did is we removed the radioactive source from the Geiger Muller tube. So now the only thing that can trigger our events in the Geiger Muller tube are high energy cosmic rays, such as muons. Now, this is pretty interesting because it allows us to essentially measure particles that aren't necessarily from a radioactive source, but are still in the environment around us from outer space. So pretty cool. Now you can see here what we did. We have these settings, 500 volts at the high volt, the gate voltage and the distance were the same. Then we collected 50,000 samples, giving us 50 milliseconds at each measurement. And you can see the reduced chi-squared here was actually very low. So this is good. This means this is a pretty good fit. And furthermore, this actually just intuitively looks like a Poisson distribution where we have a shifted mean that's at the lower end, as opposed to a Gaussian distribution or a binomial distribution. So moving onward, we put the cesium source back in the Geiger Muller tube, and we're able to measure a Gaussian distribution now. And again, this is to be expected because of a lot of reasons, but particularly because of the particles that are being generated here. So we measured the mean and the standard deviation as seen, and the standard deviation of the mean across various trials. So here was the settings that we used, and we had 1,000 samples, each giving a gate time of 6 seconds. So this is pretty interesting. By just increasing the gate time to 6 seconds, we end up with a Gaussian distribution as opposed to this Poisson distribution, which has a lower amount of counts. Now, I should be careful though. It's hard to compare these two because when we were doing this with the Poisson distribution, we didn't have the cesium source. So maybe I should redact that statement. All right, so a binomial distribution can also be seen, and we actually had the same settings here that you saw previously, I'm not sure actually the number of counts here. I assume it's reasonably high. Yeah, you can see it's well over 30, so this is enough to produce a good distribution. And you can see the reduced chi-squared here for the binomial distribution is decently low, so this isn't a terrible fit. And You can also verify this by looking at the p-value. It's very, very close to 0. So, all right, I think that wraps up the binomial distribution. Moving into an additional study that I looked at from the data that we had, I basically plotted how does the average count versus the threshold voltage change. And I thought this was pretty interesting because we expect at a certain value, the threshold voltage will be so low, so high that our system actually isn't being triggered unless we, I don't know, have some much higher energy particle enter the tube. And you can see that that occurs here. We go from having a decently high count to a much decreased count at some voltage between 1500 and 1700 volts. I think this is the reason why we're still getting a count here is because we actually do have higher energy particles still coming from the source that are able to trigger this much higher one. But as you can see, there's like a discretized change that must occur. So maybe these are beta particles that we see here, and these are actually gamma particles. I'm not entirely sure. So that's all I have now. Unfortunately, I wasn't able to figure out how to calculate the mass of a particle, or sorry, the mass of the radioactive source based on the solid angle that we receive. And I do know, I'm pretty sure this is possible, and that's how you would calculate the mass of the radioactive source if you weren't given a lot of time. Now, an alternative experiment to mention, though, is how you could measure the half-life given an ample amount of time, is to just let this experiment sit and run for, a long time, several years or months maybe, and look at how the number of counts changes over that time. The radioactivity of your source will change, and you can use this to measure radioactive decay. Now, I'll write out the equation just because it's one that we've all probably seen before, but the activity as a function of time is just going to be equal to the initial amount we measure whenever we start our experiment times some decaying exponential, which decays at some rate as a function of time. So this is the equation. And for the half-life, we would essentially measure, well, when does A of t, so if A of t equals 0, or sorry, 1/2 of A naught, then we're at the half-life. Now, if we measured this for a couple months, maybe we didn't end up with half of the activity, but instead we ended up with, I don't know, 98%. We could still use this equation to accurately discover what the half-life would be. So it's kind of interesting stuff. And that's my presentation. Again, thank you for watching.